Good afternoon, Michael.
Good afternoon, Michael.
Great to see you.
Welcome to my lesson today. Today, we will be going over true airspeed.
Oh,
Okay.
my favorite.
Now, this is very pertinent to us today because we are planning our first cross country to Ludington.
Okay.
And going to Ludington, our true airspeed helps us find our ground speed,
Mm-hmm.
which will tell us the exact time it's going to take us to get to our destination.
All right.
Okay? So, as we calculate that airspeed, you need to know first that true airspeed is the speed that we are traveling through the air. Okay? Now this airspeed would be identical to ground speed if there's no wind. Okay? So it corrects for the wind that is in our atmosphere.
All right.
I want to draw out the first thing we need to do to get our step towards our true airspeed is find our pressure altitude. But first, I kind of want to discuss pressure because it'll help you grasp what we were talking about more. I'm going to draw a parcel there. Okay? We are going to call down here the surface. SF for surface. And up here we'll call it flight level, call it 60,000 feet NSL. Okay. Down towards the bottom here. Our molecules in our atmosphere are a lot closer together. The air is a lot more dense. Okay? We start getting up higher in altitude, and you can see the air molecules are a lot further apart. Now this can change day by day or change with altitude. Different temperatures cause the pressure in the air to change. So if it was a cold day, let's say we're up here, let's say it's super cold, the air is getting pushed together, causing the air to be more dense, causing what I'll show you after we compute our true airspeed, that flying in more dense air will actually slow down our true airspeed versus flying warm air. It'll speed it up because we have less molecules to fly through. Same as going low and going high. If we're going low, our true airspeed will be lower, and if we're high, it will read faster.
All right.
Okay? So now, to calculate our pressure altitude, we need a few basic pieces of data that we can get from our METAR. Okay? I'm just going to kind of make it up for today's lesson. So, our temperature at our airport is 20 degrees Celsius. And we got our altimeter setting, again, from our METAR, being 3042. And our route to Ludington today, since we're going west, west is best, even plus 500. We're going to be using 6,500 feet MSL for a cruising altitude. And we're going to standard temperature, lapse rate, and based on our POH, and since we know our aircraft, we know that our calibrated airspeed today will be around 102. Okay, so now let's get into calculating our pressure altitude. This is the easiest one, in my opinion, to calculate. What we're going to do is we're going to take our standard atmospheric pressure, being 2.9er, 902, and we're going to subtract the standard from our current, which is our altimeter setting. So our current one is 30.42. After we subtract that, we get a negative 0.5. Okay, now after we get this negative 0.5, we multiply this 0.5 by 1,000. And the reason we are multiplying that 0.5 by 1,000 is, again, because standard lapse rate, but not in temperature, we're going pressure. 1 inch of mercury will decrease every 1,000 feet you go up in the atmosphere. So after we do negative 0.5 times 1,000, we get a negative 500. Okay, So what we do from here is we're going to subtract this 500 from our cruising altitude to get our pressure altitude at cruise flight. Okay, so 6,500 plus a negative 500 is going to be 6,000. This right here is our pressure altitude. Are you following me so far?
Mm-hmm.
Okay, very good. So now, the next step that we need to get towards true airspeed is density altitude. And this is when we're going to start using our E6B. But first, I want to discuss how we're going to be putting this stuff into our E6B. Okay, we are not going to be putting in 20 degrees Celsius into our window on the E6B because obviously standard lapse rate, temperature every 1,000 feet will be decreasing 2 degrees Celsius for every 1,000 feet. So the easiest way to do that is multiply this for how much we're going up. So we'll be going up 6,500 feet. Multiply that by 6.5. So let's do 2. 2 times 6.5 will give us 11.4. Okay, so what we do from 11.4, we subtract that from our temperature at ground level, 20 degrees Celsius, giving us about 8.6 degrees Celsius. You got how I did that? So our 11.4, I got from our standard temperature lapse rate. I subtract that from 20 degrees Celsius. Okay, you follow me?
Mm-hmm.
Good. So now we have 8.6 degrees rounded up to 9. So we're going to call our temperature at our pressure altitude 9 degrees Celsius. Okay, now let's go ahead and get into density altitude. Density altitude is first, let's talk about how it changes with different temperatures. Okay, if you're flying on a cold day, the air in the atmosphere will be condensed more. Vice versa, when it's warm, the molecules will be spread apart. A good example I like to tell my students is, think about freezing an ice cube. Okay, you put water in the freezer and it freezes. It's the most dense it can be. Now when you melt it, it gets less dense, melts apart, and you have warm water, something you want to go swimming in. Okay, that's how we compare to our density, altitude, and our parcels of air during flight and in aviation. Alrighty, now let's get going to the E6B. Okay, people are always scared of the E6B, but it's really simple to use, especially because the E6B always has directions you can follow very easily. Okay, the first thing we're going to do to get to true airspeed and density altitude is window right here, pressure altitude, thousands of feet. So we determined that our pressure altitude was 6,000 feet. And what we're going to do is we're going to set our pressure altitude opposite of our temperature in Celsius. Okay, so we have 6,000 feet. After the 5 there, it goes by thousands, so 5, 6. We're going to line the 6,000 up with 9 degrees Celsius. So right there, it's 6,000 lined up with 0. 5 degrees Celsius, about 9 degrees Celsius is right there. And our density altitude is showing about 6,500. See that? Okay, and now we use our calibrated airspeed on the inner ring here. So you remember where our calibrated airspeed was? 102 knots. We look over here, 100, 102, 102. Follow that up. Now your true airspeed's on the outer ring. So you go straight up. Now we're looking at about 112, 113 knots for our true airspeed. Okay, so do you understand how I computed that? It's pretty simple. Okay, so you notice as we calculated that, like I said before, earlier in the lesson, that our true airspeed is actually faster than our calibrated. And that's because once we get to our altitude, we are higher up. And you remember that drawing I drew? The parcel of air?
Mm-hmm.
Mark is not giving me any luck here. So here's our parcel of air. Again, we got sea level down here. And we have 60,000 feet. We'll call us right about here. Okay, so again, it's more dense down here. It starts getting less dense and less dense and less dense. So as we rise in altitude, the reason our true airspeed is higher is because we have less dense air to fly through, giving our aircraft better performance through the air. We can glide better, and therefore our true airspeed can be greater. Well, Mike, I think that's about all I have for you. I hope that made true airspeed pretty easy for you, and hope to see you soon.